Hello everyone. So let's talk about sensitivity analysis for this presentation. And we'll talk about sensitivity in the context of both a minimization problem as well as a maximization problem. Okay. So I'm going to use the same example that we used in our class, right? So we have discussed this in our class, but I'm going to do this again in the video presentation. Okay. All right, so this is the problem that we talked about in the class, right? We went over the formulation. So if you have questions on the formulation, you go back to your notes. You will see how we arrived at the formulation, okay? Arriving at a formulation is not the subject matter of this lecture. The subject matter is sensitivity analysis, all right? So for this problem, that's the formulation we arrived at when we did this in class. So you put this in Lindo, you get the solution, okay? And we talked about how you can put this in Lindo and get the solution and so on in one of the graphical solution methods. So if you need help, go there and take a look at how this is done, all right? So you get the solution using Lindo. That's the solution you will get from the Lindo software, all right? So just 1 minute here. Okay, so these are various parts of the solution you get from the Lindo software. And I will, one thing at a time, talk about the different components of the solution, all right? So for now, I'm going to start with this portion. I'm going to start with this portion of the Lindo output, okay? All right, so the first thing is the solution to the problem, right? This is how you have defined a formulation, and these are your variables, right? An, Bn, and so on. And this is the solution we need. We need to find out what the values are for your decision variables An, Ao, and so on. So you solve this in Lindo and you get the solution right there, okay? So that's the solution. So make 50,000 of product A on the new line, make 40,000 of product B on the old line, and so on, right? So that's the solution. That's the first thing we should be able to do. Read the solution from the Lindo output. So next, let's talk about reduced costs. At the moment, as you see, that this variable is 0. What that means is, currently, we are not making any product A on the old production line, okay? And if you want to start making product A on the old production line, then what needs to happen? This is a minimization problem. So if somehow you can reduce the cost of making product A on the old production line, then you will start making product A. And that is what the reduced cost tells you. Reduced cost is telling you that, well, your objective function needs to improve by that amount so that this variable will start to appear in your solution. Now, in the context of minimization, improvement means a reduction in price or the reduction in cost, okay? So at the moment, cost is 40. The cost needs to improve by more than 5. So if you reduce that cost somehow to 44, then you should be able to see product A being made on the old production line, right? So that's what I did. I reran Lindo making that change. I changed the cost from 50 to 44. I improved it by more than $5. And now you can see that, well, now you can make product A on the old production line. All right, that's your reduced cost. Okay, so let's keep moving. Let's talk about the dual prices now. You have 4 constraints, okay, and these are the slack or surplus values you get from the Lindo output for every constraint. So for this constraint, this is the row that applies for constraint 1. For constraint 2, that's the row that applies for constraint 2, and so on. All right. So at the moment, I'm going to focus on this constraint right here. Okay? It says that, well, you cannot make any more than 80,000 products on the new production line, right? And the dual price for this is $15. So what dual price means is if somehow I increase the right-hand side of that constraint by 1 unit, your objective function would improve by the dual price of 15. Okay, so I'm going to improve this, I'm going to increase that, I'm going to increase by 2, and that will cause an improvement in the objective function by the dual price times 2. So objective function at the moment is that. Improvement means in the context of minimization, the cost should fall. Okay, so let's see what happens. So what I did is I increased the right hand side by 2, right? So now this is the new objective function I get. And if you find a difference between these two values, if you find the difference between A and B, right, I see that the difference is 30. So what has happened is, as you increase the right hand side, your objective function improved by $30. Right? So that's the meaning of this dual price. Okay, so if the dual price is positive and you increase the right hand side of the constraint, then your objective function improves. Another example of dual price. So now what you have is we are going to focus on a negative dual price. Okay, so this is related to the total number of product A's that you need to make. Okay, so we have to make 50,000 product A's. All right, that's the constraint. So if what the negative dual price means is if you increase the right hand side of the constraint, your objective function gets worse, right? So then I'm going to increase this number. Okay, I'm going to increase that number by, let's say, 1 or 2, right? Let me see what I have done here. What I have done is I have increased that number by 2 units. So now your objective function will get worse by the dual price times 2. Okay, because it gets worse by minus 45 for every unit increase in right hand side. I increased it by 2, so it will get worse by 45 times 2. So this is the new solution, and if you see the difference between the original and the new solution, you will see that the cost has gone up by $90. Right? So that's the interpretation of a negative dual price. All right. Now in the same sense, what happens is if you decrease this right hand side, if you decrease it from 50,000 to, let's say, by 2 units, 49,998, if you did that. Try doing this on Lindo, right? So if I reduce this, then your objective function would improve. Right? So understand how it works. Dual price says that if you increase the right hand side, your objective function gets worse. Similar when, if you reduce the right hand side, your objective function should get better. Okay? All right. So now let's talk about the range for dual prices. This is the output you get in Lindo. So that's your constraint. You got to make at least 50,000 of product A's. Allowable increase is 20,000, allowable decrease is 40,000, right? So now you can find the range value. So here is the dual price. What this says is dual price works only in that range. 50,000 plus allowable increase of 20 and 50,000 minus allowable decrease of 40, right? So your dual price is going to work only in this range. So what's your dual price then? We found that earlier, right? Your dual price is 45, and this is saying that this dual price of 45, this is going to work only within that range of the right hand side value, right? So this number could go only in this range for the dual price to be applicable. If that the total number of product A's to be made changes outside that range, then you cannot use this dual price. You need to resolve this problem. Okay? All right, that's your dual price. And finally, let's understand the coefficient range for the objective function coefficients, right? So this is your objective function now. And we will focus on this number here. This 30 means that it costs you $30 to make product A on the new line, right? Okay, so what we are trying to say is, you know, a common sense will tell you, right? If you make changes to that coefficient, then there should be changes to the number of products you make, all right? So here, you have an allowable increase of 5, right? Now, you know, if you increase that number 30, right? So if you increase this number, what is happening is you are increasing the cost of making the product on the new line. So if it's getting more expensive, then you should make fewer products. Okay, if it's getting more expensive to make product A, then you will make fewer products A on new line. But when would that happen though? For that change to happen, your cost should go up by more than $5. So that's what this allowable increase is, okay? As long as the increase is $5 or less, your solution is not going to change. So your solution is right here. This solution is going to stay the same as long as the increase in the cost of making the product is $5 or less. If the increase is more than 5, then this solution would change. So that is what we have done here. We have increased the cost by more than 5. Okay, so the cost has gone up by 6 now from earlier number of 30. It has gone to 36. And now what that did is, as you would expect, increased cost leads to a reduction in the number of A's you make on the new line. Okay, so your solution changes. But this would not have happened if you did not increase the price by more than 5. So try doing this on yourself in Lindo to verify if you need to. If this number is 34 instead, okay? So if you have 34 in there, what will happen is this solution would stay the same. This would not change. For this solution to change to this one, the increase has to be more than 5. That is the allowable increase. All right? So that's the coefficient range. Allowable increase, allowable decrease, you know. 30 plus 5, 35, right? It stays within this range. The solution stays the same. All right? So we are using this allowable increase, allowable decrease to find a range for this cost where the solution does not change. Another example of the same thing. So now we'll focus on the cost of making product B's on the new line. At the moment, it's costing me $25. Now, if you reduce that cost, same thing. Common sense will tell you that you should be making more B's. But that cost reduction should be more than allowable decrease of $5. So what I'm doing is I'm reducing the cost from 25 to 19, which is more than $5. And what that does is initially you are making 30,000 B's on the new line. Now you are making 70,000 B's on the new line. As expected, you are making more B's now because making B is cheaper on the new line. Okay? And then similarly, I am finding the range in which the solution would not change for the cost of making B on the new line. Right? So I am using these values to find the range. Okay? All right, very good. So I think that is it as far as a sensitivity analysis in the context of a minimization problem. Right? Now let's deal with sensitivity analysis in the context of a maximization problem. So let's use this problem. Very simple. Okay, and this is what we have done in the class. You know, we did this in the class, and we arrived at the formulation, right? So I should, I should correct myself here. So this is not what we did. We did not do this in class. Okay, but this is a simple thing to arrive at the formulation here. So all this saying is the cost of making A on the new line, old line, right? Cost of making B on the new line, old line. Capacity of the old line is 80, new line is 80, old line is 60, and so on. So that's the formulation for this particular one. Okay. Right? This is the cost that is given. You are trying to minimize this. You have to make at least this many of A, this many of B, and that is the capacity. Okay, this formulation is straightforward. This doesn't need a whole lot of explanation. But the next one that we are talking about, right, this one, you need a little bit of explanation on this, and we did this in class. So look in your notes, you would see how this was arrived at. Okay, so that's the formulation we got. All right. And I'm going to put that in Lindo, get the solution, same stuff, right? Lindo will give you all this output, okay? And I will deal with one thing at a time here. And the interpretation of this is very similar to what we did earlier for a minimization problem, right? The only difference is, you have to change the meaning a little bit, okay? And we'll talk about how that is done. So I will first start with the solution, right? That's the solution you get for the problem. So you essentially put this in Lindo, the formulation, you solve it using Lindo, and that's the solution you get. It tells you that make 25 product A's, don't make any product B, and make 25 of product 3, right? P1, P2, P3. 25 of product 1 and 25 of product 3, and don't make any of product 2. That's the solution. Now you are not making any product 2, right? So what would you need to do so that you can start making product 2? All right? So, at the moment, they are paying you $50 for making product 2. So common sense, again, will tell you that if they pay you more, then you should start making product 2, because now you are earning more on product 2. But how much more do they need to pay you? They need to pay you by more than $7.50. That's the reduced cost. So reduced cost tells you the improvement you need to have in the objective function coefficient so that the variable achieves a positive value. So improvement in the context of a maximization problem means your profits should increase. Okay, so that's what I'm doing next. I'm increasing the profits by more than 7.5. Here I'm increasing the profits by 8. Okay, so that's what you see here. The profits have gone up by 8. And now, earlier you were not making any P2, and now you have started making product 2. Right, so that's how you interpret the reduced cost. Okay. All right, let's move on to the coefficient range. Okay, so looking at product 1. Product 1, they are paying you 25. If they pay you less, you would make fewer of product 1, right? Because now you are not earning as much on product 1. But how much this reduction needs to be? So that's what this allowable decrease is. Okay. If they start paying you less by more than $10, then you will not make as much product 1s, right? So that is what I'm showing you here. So the reduction in the profits you are earning is more than the allowable decrease of 10. I reduced it by 11. And what that did is earlier you were making 25 of P1 and you are not making any P1 anymore, right? So that's how you interpret the allowable decrease. And then using this information here, similar to what we did in the earlier problem, I am finding the range. Okay, so here is the range then. The solution stays the same within that range. Okay? And then this sign here, this needs to be actually infinity. Right? So this is going to be infinity. Okay? So 20 to infinity. So as long as this coefficient stays anywhere between 20 to positive infinity, your P1 would not change. So try doing this in Lindo. Okay? Your coefficient needs to be out of that, the change needs to be out of that range. So this minus 19 is out of this range of 20, from 20 to infinity. And that is how you got a change in the solution. All right. So one more example of the coefficient range. Right? So now I'm going to focus on the third product. At the moment you are making this many, right? So if you wanted to make more of this, right, they need to pay you extra money. Okay? So how much more? Right? Allowable increase is 10. So this tells you that if they paid you 5 more, so if this goes up from 20 to 25, yes, it is profitable to make P3, more P3, but still it's not profitable enough to start making more. It becomes profitable enough when your increase is more than the allowable increase of 10. So as you go from 20 to 31, now it's profitable enough to start making more P3. So now you, from making 25 P3 earlier, now you are making 50 P3. And again, try to do this in Lindo, put this value as 28, for example. So there is an increase in profits from 20 to 28, but the increase is not enough. And you will see that the solution stays the same, which is this. It does not change. So then again, I can find the range in which the solution stays the same using that information. Okay? And that is what you see here. That is the range in which the solution stays the same. The solution stays the same between $15.72 to $30. If they pay you any less than 15.72, you will make fewer of P3. And if they pay you more than 30, then you will make more P3. Right? So you will make fewer P3 here, and you will make more P3 on that side. Okay? All right, so that's about the objective coefficient range. Let's talk about the dual price. So 3 constraints. This constraint relates to the labor hours available. The first 2 constraints relate to machine 1 time, second one relates to machine 2 time, the third constraint relates to the labor time. All right. Now what's happening here is, again, this is important. So this is important for other problems as well. So understand how to interpret those slack or surplus variables. So for this constraint, the related row is this one. The slack or surplus variable is positive. What that tells us is that machine 1 time is not completely utilized. Right? There is leftover machine 1 time, and the leftover machine 1 time is 8.75 hours. So what this says is that this constraint is really redundant. You don't need that constraint, because you are saying that the machine 1 time should not exceed 40. That is what you are saying. But well, you are not using 40 anyway, so it's unnecessary to have that in there. And you can try doing this. Go in Lindo, get rid of that one constraint, rerun the problem, and you will see that there is no change in the solution. Or in other words, this constraint does not matter. Okay? This constraint doesn't matter. This constraint is not binding. Now on the other hand, if you look at the labor constraint, the slack or surplus value for the labor constraint is 0. What that means is you are essentially utilizing all the labor. You are not left with any labor resource. Okay? So this labor constraint is important. This labor constraint binds your value of the objective function. You are not able to make more products, and hence you are not able to earn more profits because you are running into a labor bottleneck. You are running out of labor. So this labor constraint is called a binding constraint. Okay, so remember this word. This is a binding constraint. Okay, so they will ask you on the question, what are the binding constraints? Those constraints for which you have the slack or surplus variables as 0, those are the binding constraints. They bind the objective function. Here the labor constraint is binding our profits. Okay, all right. So the dual price is 12.5. What this says is if I increase the right hand side of the constraint, then your objective function should improve by $12.50. So that's what I'm going to do now. I'm going to increase this by 1. Okay, and let's see what happens to your objective function value. At the moment, these are the profits I am earning. Okay, so here we go. Your labor has been increased by 1. As a result, what has happened is your profits have increased. And if you look at the difference between these two profits, right, here is the difference between these two profits. The difference between these two profits is the dual price. Right, so that's what a dual price is. It tells you by how much there would be an improvement in the objective function if you increase the right hand side value by 1. Okay, the objective function here is maximization. So improvement in objective function means that your objective function would go up because you want to maximize the objective function. Now in the same vein, if I reduce the labor from this number to a lower number, then it means that it should reduce your objective function value, right? So that's what we will do next. So that's 100. Dual price is that. It tells you that if you increase the right hand side, your objective function would go up. And on the other hand, if you decrease the right hand side, your objective function would go down, right? So now I have decreased the right hand side. It has gone down from 100 to 99. And that has resulted in a reduction in profits. So if you find the difference between that number and this number here, the earlier number, you will see that the reduction is $12.50. Okay, which is equal again to your dual price. All right, so that's how you interpret the dual prices. All right, so other than that, everything stays same in the context of maximization and minimization. If I wanted to find a range for dual prices, you do the same thing that we did in the context of minimization. Okay? So thanks a lot, and this should help you solve sensitivity analysis problems on the exam.